In this practice, we're going to try to determine the density of an unknown liquid using the pressure. We have a sealed tube with a vacuum that we open up the bottom in the liquid so the liquid will flow up. And so it starts with nothing in it, but as soon as we open it, it flows up to a specific height. What we find is that the unknown metal liquid goes from the level of the liquid in the bowl up to 330 millimeters above it inside the tube. So this is the height the liquid takes inside the tube when there's a vacuum above it. It is 1 atmosphere of pressure outside. Our tube has a cross-sectional area of 2 centimeters squared. Basically the inside of the tube, if we think of area is equal to pi r squared. Our area is 2 centimeters squared, which if you want to do the math, the radius is like 0.797-ish centimeters, somewhere in line with that. Rather than make you calculate it though, we just know what the area is. So this tube has the liquid get pushed up it. How can we use this info to solve the density of this liquid? Give it a try just to solve the idea. Don't do the numbers right away. What do you need to be able to solve this? What would we have to find? Come on back, we'll go through a list of ideas, and then we'll pause and give a try. So if we want to determine this density, we have to think about what's going on. Well, that liquid doesn't want to go up the tube on its own. It's being pushed up there. If you only had a vacuum on the outside and a vacuum on the inside of the tube, there'd be no force pushing the liquid in either direction. But the atmosphere is impacting the surface. It's pushing our liquid down. And originally, when we have no liquid in there, when it's all at the same height, well, they're all trying to get pushed down, but inside the tube, there's no air. So there's air on all sides of the outside, pressing down, squishing the liquid. Well, if you're being pressed in one direction, you press equally in all other directions. And so that liquid is pressing the next liquid in all directions. They're pressing the liquid directly under the tube. It gets pressed in all directions. And the liquid in the tube gets pressed in all directions, but it's pressing up and nothing is above it. The vacuum can't press back down. So that liquid starts to move up. And it just keeps moving up and moving up. And while it moves up, well, now you have a weight of liquid inside the tube that you don't have pushing down outside the tube. So as this liquid goes up, you start building up a force inside the tube. I'll draw it on the side there, but really it's in the tube pushing back down. What will stop that liquid from rising is when the downward force of all the weights of stuff in the tube matches the upward force from all the pressing from the atmosphere. So what we really know is that at 330 millimeters, the downward force of all the liquid in the tube above the level in the bowl must match the downward force of the outside atmosphere. That blue arrow must be equivalent to 1 atmosphere. So we can find the force we must be pressing down with. Well, we want density. Density involves mass and volume. Atmospheres are not a mass unit. So we're probably going to have to convert some pressures into some mass unit that's going to be useful for us. Being that we are in metric, I'll leave you to figure out what those might be. But knowing that, can you find what density of material this volume of material would need to be to match the outside pressure? So give that a shot and come on back. All right, if you're back, well, what I've got is I have a tube and I have some pressure pushing up that is 1 atmosphere. And inside that tube, I've got some liquid. And that liquid is pushing down with 1 atmosphere. How is it doing that? Because of its weight. Remember that weight over area is a pressure. Mass over volume is our density, but pressure was force over area, and a force is a mass in an acceleration in gravity. So weight pressing down over the area it is pressing. Well, we have the area. We were told, hey, I know the diameter of my tube. What is my tube's construction? I have a 2 centimeter squared base by whatever amount of liquid is in there. 330 millimeters tall. I can convert the millimeters into centimeters, which is 33 centimeters tall, which means I can find the volume of this tube. I have the area of the base and the height. 33 centimeters times 2 centimeters squared for 66 centimeters cubed. The total volume of all the material inside that tube is equal to 66 cubic centimeters of material. That is the volume of this unknown liquid that is in our 330 millimeters of height in this particular tube. So I have my volume, which is part of my density. I need my mass. I need my mass there. Well, think about our pressure. There's a lot of pressure units. There's 1 atmosphere. There's 14.7 pounds per square inch, which has a weight and an area, but we're in metric. So what about 1,035 grams per centimeter squared? Or 1.035 kilograms per centimeter squared. Here's one in metric. This one's going to be a little bit easier for us. I can turn my 1 atmosphere into 1,035 grams per centimeter squared pushing liquid up, and I can turn my liquid pressure into 1,035 grams per centimeter squared pushing down. This is when they'd be equal and your height would stop going up. Well, that means all the material I have must be 1,035 grams per centimeter squared. Well, my base is 2 centimeters squared. I can actually figure out what my weight is by knowing what the downward force must be and knowing the volume and knowing the area it is pressing down on. I can say, well, my base is 2 centimeters squared. I know for every 1 centimeter squared, I would have to have 1,035 grams of material. I have a bigger base, so there's just more weight. I did think back to when we talked about gases and we talked a column all the way to space. 1 inch by 1 inch. And in that column, all the way to space, normally in the air there is 14.7 pounds of air. If you just draw a second column right next to it, effectively I've just doubled my base. It's now 2 inches across 1 inch tall, and this one also has 14.7 pounds. If you have twice as big a base, you just have twice as much stuff in the column you make, which is what we find when we do the math. For having twice as big a base as we normally write them in, well, we'll multiply our mass by 2, so 2,070 grams. That is how much weight must be in our tube. There must be that weight of material pressing down on the 2 centimeter square base for it to make the equal pressure from the outside. So I know my grams. I can now plug that in because I know my grams and my volume. I have 2,070 grams and a volume of 66 centimeters cubed for all of the liquid in that tube. Divide those by each other. And what we will find is that this must be 31.4 grams per milliliter. And so we can find the density of this unknown liquid. Does this make sense? Well, let's take a second to think about it. If we had mercury, mercury has a height of 760 millimeters of mercury when you're 1 atmosphere. Mercury has a density of approximately 13.6 grams per milliliter. So mercury, it weighs a lot, and it only goes up about 76 centimeters. 33 centimeters is less than half that height. That means you have to have the same weight of material, but in less than half the volume. Well, if you have less stuff for the same weight, you must be more dense. And that's what we see. We say, hey, 31, well, that's a little bit more than double the density of mercury, which would give us a little bit less than half the height of mercury. So this seems fairly reasonable for the height that we saw this metal go up. Now, what metal could do this? It's a theoretical one. It's not any real metal. It's just we needed a very dense subject to discuss this with. But this is how we could calculate it. And we could similarly do this for any liquid. Second problem, find height of H2O, so 1 gram per milliliter, in a 2 centimeter square based tube if 1.0 atmospheres outside. So this time, instead of taking the height to find the density, here's a density. Find the height we expect the liquid to go up the tube. Go ahead and pause and give that a try. All right, if you're back, well, same setup. I've got liquid, I have a tube that's going to go up, and there's going to be some height to it that it fills with liquid. I've got a bunch of gas on the outside impacting the liquid. It's 1 atmosphere outside. So the pressure going up the tube, but just think about the tube, the up pressure is 1 atmosphere again. And if I get to a certain height, the down pressure must also be 1 atmosphere. We can convert our weights again. 1,035 grams per centimeter squared would be the up pressure, and 1,035 grams per centimeter squared must be the matching down pressure. Again, our tube, we said, was 2 centimeters squared. So I have some volume that we don't know yet, where the total mass of it, well, I have 2 centimeters squared base, and for every 1 centimeter squared base, I must have 1,035 grams of material. So again, I need 2,070 grams of material. Well, we know the density of water. 1 gram of water is 1 milliliter. I have my grams, I can find my milliliters. 2,070 grams is the volume or the weight my liquid must be. I know that for every 1 gram of water, it must be 1 milliliter. So this tells me I must have 2,070 milliliters of water. That is the total volume. Well, what is my volume? It's going to be x centimeters tall by 2 centimeter squared. A milliliter, 1 milliliter, remember, is 1 centimeter cubed. It's just another way to describe the same unit. So 2,070 centimeters cubed must equal 2 centimeters squared times x centimeters tall. Divide the 2 centimeters squared on both sides. What we'll find is that the x centimeters tall is going to be 1,035 centimeters. Since the density of water was 1, all of our multipliers are by 1. And so we just end up with a height equal to the weight. Rather convenient for water. It's part of why it's nice that everything's based on water. The result, though, is that this is 10 meters. 10.35 meters tall. So over 30 feet, you can't exactly have a tube like that in a classroom. And so this is why we don't use pressure measuring devices with water inside. They have to be the height of a building in order to have an effective measuring capacity. Well, this is how tall up water would have to go in a tube to counter 1 atmosphere of pressure outside. This is also why this is the highest you can pull water up a tube. If you put a vacuum in a tube, the water will rise about 32 feet up the tube before it stops, because that's where the outside pressure can push it to. The only way to get it to go higher would be if the outside pressure was greater.